Learning objectives. At the end of this topic, you will be able to understand about irrational numbers, solve problems on irrational numbers, describe revisiting rational numbers and their decimal expansions. Before we prove that root 2 is irrational, we need the following theorem, whose proof is based on the fundamental theorem of arithmetic. The prime factorization of A equal to P1, P2 and so on up to Pn, where P1, P2 and so on up to Pn are primes. Hence, A2 is equal to P1, P2 and so on up to Pn into P1, P2 and so on up to Pn. That's equal to P21, P22 and so on up to P2n. That's equal to P21, P22 and so on up to P2n. Now we are given that P divides A2. Therefore, from the fundamental theorem of arithmetic, P is one of the prime factors of A2. However, using the uniqueness part of the fundamental theorem of arithmetic, we realize that the only prime factors of A2 are P1, P2 and so on up to Pn. So, P is one of P1, P2 and so on up to Pn. Now, since A is equal to P1, P2 and so on up to Pn, P divides A. We are now ready to give a proof that root 2 is irrational. The proof is based on a technique called proof by contradiction. Let's assume that root 2 is rational. So we can find integers r and s not equal to 0 such that root 2 is equal to r by s. Suppose r and s have a common factor other than 1. Then we divide by the common factor to get root 2 is equal to a by b, where a and b are co-prime. So, b root 2 is equal to a. Squaring on both sides and rearranging, we get 2b square is equal to a square. Therefore, 2 divides a square. Now by Theorem 3, it follows that 2 divides a. So we can write a is equal to 2c for some integer c. Substituting for a, we get 2b square is equal to 4c square. That is, b square is equal to 2c square. This means 2 divides b square, and so 2 divides b. Again using Theorem 3 with b equal to 2. Therefore, a and b have at least 2 as a common factor. But this contradicts the fact that a and b have no common factors other than 1. This contradiction has arisen because of our incorrect assumption that root 2 is rational. So we conclude that root 2 is irrational. Let's work some more examples. Begin with example 1. Let's prove that root 3 is irrational. Let's assume that 3 minus root 3 is irrational. Let's move to the next example. Let's assume that 2 root 2 is irrational. Let's move to the next example. If r is a positive rational number and s is a positive integer greater than 1, prove that an is a rational number. We know that product of two rational numbers is always a rational number. Hence, if a is a rational number, then there are some numericals for you to try out yourself. Prove that 5 plus 5 root 5 is irrational. Let us assume to the contrary, that is, 5 plus 5 root 5 is irrational. Thus, there can be two integers p and q not equal to 0, and a and b are co-primes so that 5 plus 5 root 5 is equal to p by q, which becomes 5 root 5 equals p by q minus 5. Since p and q are rational, so p by q minus 5 is rational, and hence 5 root 5 is rational. This happened because of a faulty assumption. Hence, 5 plus 5 root 5 is irrational. Prove 1 by root 3 is irrational. Let's assume to the contrary, that is, 1 by root 3 is rational. Thus, there can be two integers p and q not equal to 0, and p and q are co-prime so that 1 by root 3 is equal to p by q. P root 3 is not equal to q. Tends to p root 3 equal to q. Squaring on both sides, we get 3p square is equal to q square. This means q square is divisible by 2, and hence p is also divisible by 2. This contradicts our earlier assumption that a and b are co-prime, because 2 is at least one common factor of p and q. This also contradicts our earlier assumption that 1 by root 3 is rational. Hence, 1 by root 3 is irrational. Prove 8 plus root 2 is irrational. Let's assume to the contrary, that is, 8 plus root 2 is rational. Thus, there can be two integers p and q not equal to 0, and p and q are co-primes so that 8 plus root 2 is equal to p by q, where root 2 is equal to pq minus 8. Since p and q are rational, so p by q minus 8 is rational, and hence root 2 is rational. But this contradicts the fact that root 2 is irrational. This happened because of our faulty assumption. Hence, 8 plus root 2 is irrational. Let's explain the statement formally. We need the following theorem, whose proof is based on the fundamental theorem of arithmetic. From the discussion above, we can conclude that the decimal expansion of every rational number is either terminating or non-terminating repeating. Summary. Let's summarize the topic. Theorem. Let P be a prime number. If P divides A2, then P divides A, where A is a positive integer. Rationals and the irrationals together make up real numbers.